H2 plus molecule ion, part 4. Now, before we start on our calculation of the energy of the system as a function of internuclear distance, let's consider what we expect that energy function to look like as a function of internuclear distance based on some simple arguments. First of all, let's consider the case where the internuclear distance is very small. For this case, we expect internuclear repulsion to be the dominant term, right? Both of the nuclei are going to be very close to one another, and the electron's going to be hanging around, but it's going to be a much less dominant term, and so we expect that our energy should be roughly 1 over big R in atomic units. Similarly, if we consider the case of big R, or internuclear distance, being a very large number, then the system would be like the hydrogen atom. Right? We would have an electron and in orbit with its nucleus, and then there would be another nucleus, but it's so far away it doesn't really matter. So we would expect that energy would be equal to the 1s hydrogen atom energy. And then somewhere in between, based on what we know about molecules, we might expect a roughly parabolic harmonic oscillator type potential where our energy is going to be given by a constant plus 1/2 k times the displacement squared, where k is a force constant. Now, what is this other constant here? We would expect that constant to be equal to, it's going to tell us something about the molecule, right? It's going to tell us something about the energy of the molecule. And we think that if we think about that for a minute, we expect that constant is going to be the bond energy of the system or molecule. So taking our thinking above and trying to distill it down into some kind of graph, we might expect that our energy is a function of R. So energy would be along the y-axis, and R would be along the x-axis here. We expect E of R to be this kind of curve, where at very short r, we have this strong repulsive interaction corresponding to a large value of E of R. And at long distances, we expect to get the 1s energy. So as r goes to infinity, we expect the energy of the system to asymptotically approach E1s. And then in between, we expect there to be a potential well that looks a little bit like a parabola, and that's what I've sketched here. And then there's this energy difference between the minimum of the parabola and that E1s energy given by the dotted line, and that we would expect to be the bond energy. Also, it's worthwhile noting that the minimum, that's going to be R sub E, that's going to be our equilibrium internuclear distance corresponding to the bond length. Okay, so now let's go on to our calculation of energy as a function of R. There's going to be a couple of components here. One is the Hamiltonian, written here in atomic units. It's minus del squared over 2. That's the kinetic energy of the electron term. Right, so we can call it del squared sub E, where E are the coordinates of the electron, minus del squared sub E over 2. And then there's going to be this Coulomb attraction between the electron and nucleus 1a. So there's going to be a minus 1 over R1a term. And then there's going to be this attractive interaction between the electron and nucleus B. We'll call that the R1b term. And there's this internuclear repulsion. That's going to be a plus 1 over R term, where that's capital R. And as we specified above, we're initially going to work through just one of these two wave functions, psi sub g, and we previously showed that it's given by this expression, where that 1 over square root of 2, 1 plus s, the s is this overlap integral that we talked about previously, and showed what the final result is for that integral, the normalization integral. So we have the two components then that we need to calculate our variational energy. So our variational energy is this Eg sub r, and it is given by an expectation value integral that looks like this. And psi g is our wave function. Now we can plug in this functional form above for our psi g into the integral. There's going to be two copies of this 1 over square root of 2, 1 plus s. And so we'll go ahead and move that outside the integral. So we have two of these multiplied together, so that gets rid of the square root sign. So we have 1 over 2 times 1 plus s here. We need to keep track of normalization. And then we're going to have 1sa star plus 1sb star. And then our real Hamiltonian. And then our approximate wave function again, psi 1sa plus psi 1sb d tau. Now we have to expand, use FOIL, distribute, and we're going to get several. We can break this up into several different integrals, 4 of them. And again, we're still going to have this 1 over 2 times 1 plus s that comes from the normalization constants in front of each wave function. And then we're going to have psi 1sa h, psi 1sa. Then we're going to have this integral psi star 1sa h psi 1sb. And then this next one, psi star 1sb h psi 1sa, integral over that. And then the final integral is integral of psi 1sb star h psi 1sb. And then we're going to introduce this shorthand. We're going to call this first integral here HAA. Notice we don't have a caret on the h anymore. This is just going to be a constant or some function that we're going to calculate, and we'll call that function HAA. It's a piece of the expectation value for this Hamiltonian. And then of course here we'll have HAB. That's going to be the second one. The third one is going to be HBA, and the fourth one is going to be HBB. And then just to make things clear, I'm defining HAA as this integral, and I'm defining this integral at the bottom of the screen here, and then this one that just popped up, HAB, is going to be given by that integral, and so on. So it looks like we have to deal with 4 integrals. And unfortunately, none of them just sort of magically goes to 0 in this case. However, there are some symmetry arguments by which you can say that HAA has to be equal to HBB and HAB has to be equal to HBA because we're dealing with the psi 1sa and psi 1sb are identical wave functions just shifted in space, right? And so based on the symmetry of that arrangement, we can reduce the number of integrals that we have to evaluate down to just two of them. So let's go through the HAA calculation. We're actually going to do this in pieces. First, I'm going to act the Hamiltonian here on the 1SA wave function. And then later, I'm going to left multiply by psi star 1SA, and then integrate, and then that's going to give me our HAA. But first, we're going to just act this on this wave function. And the reason why it's good to do this in steps is that we notice that these first two terms in the Hamiltonian, the minus del squared over 2 and the minus 1 over R1A, those are the Hamiltonian for a hydrogen atom placed at nucleus A. And psi 1SA is the solution to the Schrodinger equation for a hydrogen atom at position A. Therefore, these first two terms of the Hamiltonian are going to just give us E1s, which is the energy of a hydrogen atom in the 1s state. So this simplifies our Hamiltonian a little bit. We're going to get this E1s minus 1 over R1b plus 1 over R, all within brackets, to the left of our wave function, to the right, which is psi 1sa. Now we can left multiply by psi star 1sa and integrate, but some of these integrals are going to be simpler. E1s is a constant, so it moves outside the integral. Also, R is a parameter, which we can treat roughly as a constant. It's a constant of the integration, so we move that outside the integral, right? And that's part of the Born-Oppenheimer approximation that we introduced earlier, treating R as this variational parameter. And so our HAA ends up being this E1s plus 1 over R. And again, we've left multiplied by psi 1sa, and so we have an integral of this E1s is multiplied by integral of psi star 1sa, psi 1sa, and because those 1s or 1s atomic orbitals are normalized, those integrate out to 1. Similarly, we get the same thing happening with this 1 over R term. But we still have this integral of psi 1sa star times minus 1 over R1b times psi 1sa, the integral of that over all space. We're going to collect some terms here and call the 1 over R part, and the leftover integral, we'll call those J. And we'll see what that integral result is in a minute. But then this allows us to obtain this fairly straightforward result for HAA. It's E1s plus J. And we are not going to work through the actual integral, but we will show you what the actual final result is. This integral ends up being, can be evaluated and gives a simple analytical expression, and it's J equals e to the minus 2R times 1 plus 1 over R. And this J is everywhere positive. And so based on the fact that it's positive everywhere, we can think of J as roughly being mostly due to internuclear repulsion. But there is some effect of the electron being shared between the two nuclei. So there's some screening going on, but mostly here we're seeing internuclear repulsion. Now let's look at HAB. We're going to use a similar approach, but I'm maybe even going to give a little bit more detail here. So we're going to act our Hamiltonian on psi 1sb, right? Because HAB, you may recall, is this kind of sandwich where on the left-hand side we have psi star 1sa, then we have the Hamiltonian, and then we have psi 1sb. Okay, so first we act H on our 1sb. And then again, two of these terms of the Hamiltonian are going to give us E1s, And we're going to have left over this minus 1 over R1A term and this minus 1 over R term. And then we end up with E1S times this integral psi star 1sa, psi 1sb. We've already seen that integral before, that's s. And again, we're going to have this 1 over r term here times this integral of psi 1sa star psi 1sb. That again also gives us s. So that part of this integral is kind of already taken care of. And then we're going to still have this leftover term, which is integral of psi 1sa star minus 1 over r a psi 1sb. And of course, there's a d tau, which I have omitted for the sake of reducing clutter a little bit. And so then applying what I said above, we get that this equals E1s times s plus s over r plus this leftover integral part. And we're going to call s over r plus this other integral, we're going to call that k. And so our HAB is then E1s s plus k. And this is a somewhat complicated integral. Fortunately, there is an analytical solution, and this solution is s over r. Again, s over r, we saw where that came from, minus e to the minus r times 1 plus r. Now, if we look at this, depending on the value of r, right, this first term is positive, the second term is this e to the minus r term is negative, and it's not clear which will win. It seems like at very short distances, k is going to be positive. At some other distances, it's going to be negative. And so we can think of k as including some internuclear repulsion, but it's also including this bonding interaction. But again, that's just, k just sort of is what it is. It's various terms in this integral, but we can think of qualitatively it's representing this bonding interaction. Okay, so then if we put all this together, our EG as a function of internuclear distance is again given by this expectation value of the Hamiltonian using the wave function psi sub g. And that gives us this 1 over 2 times 1 plus s times 2 HAA. Again, that's taking advantage of the fact that there's a symmetry in that HAA is equal to HBB. And similarly, we have 2 times HAB. And again, those are the integrals that we worked through above, or worked through at least in a qualitative sense above. So putting all of that together, first of all, there's a cancellation of 2's there, right? We got 2's in the numerator and a 2 in the denominator. And we're going to get E1s plus j plus E1ss plus k, all divided by 1 plus s. And we can group some terms together. We're going to get E1s times 1 plus s plus j plus k all over 1 plus s. And there's some additional cancellation we can do there, and we get Eg is equal to E1s plus j plus k over 1 plus s. Then the question is, based on our previous discussion, what is j plus k over 1 plus s? What does that physically represent about our system in some sort of chemical sense? And the answer is, it's telling us about our bond energy. Right? Previously, we stated that our total energy is going to be the 1s energy, that's the energy at r equals infinity, plus this bond energy term. And so that's what this j plus k over 1 plus s is telling us. So that's useful. So we can calculate the total energy of the system, and we can also calculate an important piece of the energy of the system, which is what is this bond energy? and we have an expression for that. But we're not quite finished yet, right? Now we have to apply the variational approach and determine our bond length and determine our energy of the system at the equilibrium internuclear distance. So our approach is we're going to set the partial derivative of the energy with respect to R equal to 0 and solve for R. So that's going to essentially minimize the energy. We'll find what value of R gives us the minimum energy. And that gives us, when we turn the crank, that gives us RE equals 2.5 Bohr, or 2.5 times A aught with the Bohr radius, or 0.132 nanometers, or 1.32 angstroms. And that's significant. This is our first quantum mechanical estimate of sort of what a bond length should be based on the properties of atomic orbitals that we use to make up this molecular orbital. And then if we plug that RE back into EG, we get E1s minus 0.0661. E1s would be half of a minus a 1/2 Hartree. And so our answer is our total energy answer is minus 0.5661 Hartree, or minus 15.4 electron volts. That's the amount of energy that would be required to remove an electron from this system. Now, the energy that is required to pull one of the nuclei away to sort of break the bond is going to be this bond energy. And again, that's the J plus K over 1 plus S. And that, of course, is this minus 0.0661 Hartree, or about 1.8 electron volts, or about 170 kilojoules per mole. From experiment or from higher level theory, such as applying Hartree-Fock to the system with a larger basis set, we get that the actual equilibrium internuclear distance is about 2.00 Bohr, or about 0.106 nanometers, so a little bit shorter than our estimate. And the bond energy that's obtained, again, from a higher level calculation or from experiment is minus 258 kilojoules per mole. So there's a fair amount of error in this calculation. Nevertheless, we're off by 20%, 30% in the bond distance, and we're off by maybe a little bit more than that in terms of what the bond energy is. But we still were able to use this fairly simple approach to get us at least within the ballpark of the right answer. And of course, we can improve the answer by using a larger MO-LCAO, including maybe some 2S character and some 2P character in our overall wave function. And that's going to give us more parameters to optimize. It's going to be a trickier problem, but it's going to give us a more accurate answer. And that's all I have to say for part 4.